welcome everybody. We're very excited to have the FDL Europe community join us here today. Everyone joining online as well from around the world. We're about to kick off quite a remarkable 2 hours of research in AI and space science. And of course, we're thrilled that you can join us here today. First of all, just like to do a welcome from us, the FDL team, and also Pierre Philippe from ESA's Pfleet, who's one of our key stakeholders for the FDL program in Europe. But also I'd like to do a shout out to our colleagues at the SETI Institute. We're streaming live over their network today, as well as YouTube, and of course streaming from the FDL website itself. So welcome everybody. It's really great to be here to be able to share this work. My name is James Parr. I'm the director of FDL. And I was going to kick off with just talking a little bit about the FDL program, just for those who are joining, and just to give you some situational awareness, as we say, about FDL. FDL is 5 years old. It's a AI and research organization. The idea of FDL is we bring people who know the problem, so domain specialists and from the space sciences, and we pair them up with specialists in machine learning. And then we give them a lot of resources from our partners, Google, IBM, Intel, and others, and of course NVIDIA, who you'll hear from later on, and they make magic in a very short period of time. So these are the results. I'm really thrilled that you can join us here today. Again, the other thing which is perhaps useful to know about our work is we're really trying to do work that makes a difference to all of us here on this blue marble. As our sort of patron saint, I guess if you could say he's a saint, Carl Sagan says that we are living on this very, very fragile blue marble suspended in a sunbeam, as the quote goes. Really all the work that we're doing at FDL is to try and make a material difference to life on Earth, but also our future amongst the stars. I'd also, before we kick off, like to invite our colleague Pierre Philippe to give us a bit of a welcome from the Pfleet. The Pfleet at ESA in Frascati is one of our key partners, and I'd like him to kick things off with just telling a little bit about what they do there.
Okay, many thanks, James. Can you just confirm you can hear me?
Loud and clear.
Okay, so first of all, I'm very excited to be with you guys tonight. I'm actually on holiday, but I couldn't miss the FDL show. The Pfleet has been created a few years ago by our director in order to bring more innovation to ESA, to look at what is called disruptive technologies, and we identify AI as the most powerful one in order to transform the way we use and store Earth observation, because it provides new ways to do scalability and processing of the data and extract the information. And then we discover FDL, which appeared to us as the best mechanism and vehicle to bring demand and supply of AI talent to solve all these problems. And we were really impressed by the previous editions. Because it really delivers results of top quality and peer review papers. And this edition is also very, very interesting because it tackles problems which are relevant for our climate, but also for a new initiative that we call the Digital Twin Earth. So I'm really looking forward to the results. You were talking about magic, and this is exactly what happens. This is a very small time scale. And necessity creates innovation here, and we get very, very innovative solutions to problems that we couldn't solve with the traditional way. So again, thank you to everybody and the whole team to make that happen, and looking forward to the next steps.
Thanks, Pierre Philippe. So the two projects which are supported by the Pfleet are Clouds and Aerosols and Digital Twin for Earth, which Pierre Philippe mentioned, and you'll hear from them very soon. But also wanted to talk a little bit about the context where we really want to figure out how to use machine learning for better planetary stewardship. This is, if you like, the bigger goal of FDL. And thanks to the work and partners at ESA, we're starting to move the needle on this. And this is really the portfolio of capacity that we've built over the last 3 years. Last year we had great success with the cloud classifier. We've created methodologies for informal settlement detection. We've also shown it's possible to apply machine learning to post-disaster assessment. And just recently, the team published some work on showing that it's possible to do flood mapping from a edge satellite. So this is using machine learning in low Earth orbit, which of course is the future and opens up a huge world of possibility. We also have another ESA stakeholder, and this is the mission operations at ESA ESOC, and we'll invite Alejandro Donate to talk a little bit about that in a little bit, but we're also really thrilled to be able to work with them on problems that are important to mission operations. And the team you'll hear from are really looking at this problem, which is showing a mega constellation. This is the Starlink mega constellation. And you can see here that this is a lot of objects which mission operations has to track. And of course, you may be aware that there was a conjunction event late last year between Starlink and ESA. So this is one of the problems that you'll hear about later on today. And again, we're trying to build a portfolio of capacity with ESA ESOC, and this is the second project we've done with them, and the last one last year was on ground station pass management, which was a really thrilling and exciting project, and we're really happy to be able to work with that team as well. So a little bit of context about today. We're also joined by some really great friends of FDL. I'm really thrilled to have you guys join, and even though it's a little bit like American Idol or America's Got Talent or Britain's Got Talent, it's not really the idea. The idea is really just to provide some feedback, some ideas, some suggestions on next steps. And I'd like to introduce you to Alison, who's AI developer relations from NVIDIA, Julian Cornebys, who's the honorary associate professor at UCL, and Matthew Mascara, who's technical director of AI at Google Cloud. So I don't know if you want to quickly say hi, everybody, but very great, really happy for you to be here to help us, provide some feedback for this work.
Hi everybody, it's just an absolute honour to be here.
Thanks, Alison.
It's a real delight to be
here. Sorry.
Yeah, well, they both said, and really glad that some of my previous teams were able to participate in FDL. It's always mind-blowing, so really glad to be here.
And that was a good mic check.
Hello, everyone. I'm very excited to be here. I'm looking forward for the results.
Thanks, Massey, and really, I'll talk about this a little bit later, but we couldn't do it without you guys, and really, again, so thrilled that you could come along on the ride with us. But also, we wanted to make today's session interactive for the audience, and we have every year we do some awards for the work of FDL, and FDL is not a competition. It's not we're not competing for the best results, but we do like to just give a nod to, if you like, what makes innovation like this special. And so we celebrate, if you like, the methodologies that make for great and world-class work. And so this is what these awards are for. And we have two awards which we're going to asked our faculty to vote on. And this first one is Collaborative Spirit. The second one we've asked our faculty to judge on is the Heroic Comeback, and you'll hear what they decided at the end of this presentation. But we have three awards that we'd like you to contribute to as the viewing audience. And so the first one is the most dramatic pivot. So if you know about startups often start off with one idea, and then halfway through their startup phase, they realize that actually there's another opportunity that perhaps is better, or perhaps they realize that somebody else has already done it. This exactly always happens with FDL. And sometimes those pivots are small and sometimes they're large. And so as you're listening to these presentations, we invite you to decide or determine which one's the most dramatic. And you can vote on this, and you can either use this barcode to go directly to the voting site, or if you go to fdl.ai, it's there on the site now, and I think it's also in the chat of some of the other streaming channels. So hopefully you can figure out how to get to this, and please do. We really want to see what the audience determines is the most dramatic pivot. And you can see this award is also brought to life by an asteroid being moved out of the way. This is what that award's showing. Excuse me. The second award that we'd like you to contribute to is the most useful contribution. And so this isn't necessarily a scientific contribution, although you could judge it as that. But when we're doing these projects, there's a vast amount of, if you like, an iceberg underneath the surface of really, really useful work that the teams do, everything from data prep to the production of enhanced data products, synthetic data products, or just making code bases and other tools available for the community. And so please have a think, have a listen to what the teams are talking about, and we'd like to hear what you think is the most useful contribution. Lastly, unexpected discovery, which is symbolized by this three-ringed planet. And this is, of course, we are in the business of science, and every so often something magical happens where we get a little glimpse of something new. And this has happened in the history of FDL. We've had this a few times, and we're always really happy when this happens. And I think you'll find there's some of these things have happened this year as well. And so we'd like you to vote on what you think is the most unexpected discovery. So that's how that interactive is going to work. And has anyone got any questions or reflections? All right, I think we're good to go. So I also wanted to really talk about why it's so important that we have commercial AI partners working with us. As Pierre Philippe said, we do work extremely quickly, and the models we use, the machine learning models and the data sets are enormous. Really 5 years into FDL, our models are becoming very large. In fact, they're approximately 700 times faster than they were when we started. Sorry, 700 times bigger than they were when we started. And if you know about Moore's law, where computing power doubles and halves in price, doubles in speed and halves in price every 18 months. The equivalent for machine learning is every 3 months. And so we're really in this incredible revolution. And so we're happy and thrilled that we can have great partners like NVIDIA and Scan who can provide this infrastructure for us. And this is the DGX one, which 2 of our teams used, and very grateful for the team at Scan for making these boxes available. And it really is like a supercomputer in a box. It's an extraordinary machine, and the teams are able to do things very rapidly. The other compute partner that we've used this year is Google Cloud, and really it's hard to imagine how we do the work without them when you're integrating data sets from around the world, and of course working on very complex pipelines. It's very difficult to do this work locally. A cloud provider is really where a lot of this effort gets done now, and Google really makes this seamless. And it's again not only that, they provide a lot of guidance, and they're a great team as well. So just wanted to give a little bit of a background to the compute resources we use, and then before we jump into clouds, I wanted to sort of give a chance to Pierre Philippe to introduce the team. I mean, I know Pierre Philippe, you're an atmospheric scientist, so I thought this would be much better coming from you than me.
Yes, in fact, I'm actually oceanographer, but because the atmosphere and ocean are so coupled, we have this issue as well. And as you know, cloud is one of the biggest challenge for climate modelers, because most of the uncertainty comes from understanding what's the behavior of clouds, their height, their shape, their properties, optical properties. And FDL did a great job last year in building a data set that the community can use. And this was for me really disruptive, because the traditional way to look at cloud in our community is almost simple statistics about if it's white or not. And having an automatic way to classify this and go through the whole archive is certainly disruptive. And this year, capitalizing on this and looking at the interaction with aerosols even make it more exciting, because both are so coupled that maybe you can learn something on aerosol from cloud and vice versa. So it's highly coupled system. And I'm looking forward to the results. I know the team has been doing a great job and has been led through very good coaching. And let's see what happens so we can better understand our climate.
Thanks, Pierre Philippe. All right. Well, I think Clouds team, are you ready?
Great, thank you, Pierre Philippe, for a fantastic introduction there. So to kick off the digital showcase, we're the Clouds and Aerosols team, and we're going to be giving you an overview of our work this summer, looking at how trying to unveil the kind of complexities of how pollution affects the behavior of clouds and the impacts of that on the climate. So to begin with, a quick introduction. We're a team of 4 researchers. We have Tim and James, who are researchers on the machine learning side of things. We have Lucas, who is a kind of cross-disciplinary climate researcher. And lastly, myself, I'm a specialist in clouds in atmospheric physics. And then we have the support throughout this project of our fantastic leads. So we have Matt Kusner, who's our machine learning lead, and Matt Christensen, who is a domain lead. And last but not least, we have our super mentor, Duncan, who's been a fantastic support throughout this project. So clouds cover a huge proportion of the Earth's surface. We all know instinctively the effect on the weather when we have clouds. Clouds make it cool, they make it mild. When it's clear, it's hot and dry. And the same is true for the climate as a whole. Clouds almost act as air conditioning for the atmosphere. By reflecting incoming sunlight, they keep the Earth cooler than it would be otherwise. In particular important are these large decks of marine boundary layer, so close to the surface clouds, that cover vast areas of the Earth's oceans, particularly off the western seaboard of all the major continents. These clouds cover a huge extent. You're looking at an area kind of similar to the extent of Europe. And these really consistent clouds have an immense impact on the climate. If we were to remove them, then the warming effect could be 10 times as large as all the warming since pre-industrial times. So even if we alter the spread of these clouds, even a small extent through our pollution, through our human activities, we could massively increase the rate at which the climate is warming. And the reality is, we know that we are altering these clouds. The challenge is knowing how much and how that will change in the future. So one of the most complex pollution that we release into the atmosphere is what we call aerosol pollution. You might also know it as particulate pollution. These particulates are released in often the same way as greenhouse gases from burning fossil fuels. So some of these we can see are natural. You'll have sand coming off the desert regions. You'll have sea salt and dust. But we'll also have soot and smoke from burning biomass. We'll have sulfuric acid and nitric acid from internal combustion engines. And the effect of aerosols upon the climate is actually a cooling effect. So in this chart here, anything that's to the right is warming. So you see carbon dioxide at the top, along with the other greenhouse gases, having a large warming effect. But we also have aerosols at the bottom, which have this cooling effect. And not only do they have a direct cooling effect, they also interact with clouds. And in fact, here, what we can see is there's a huge uncertainty, this error bar, in how large that cooling effect due to the interaction with clouds is. And that's a big problem for predicting the future of climate change, because this cooling effect acts as a mask to how severe prior warming already has been. And we can't just extrapolate that, because aerosols have a very short lifetime in the atmosphere. If we were to stop burning all fossil fuels today, the carbon dioxide we've already emitted will on average still be in the atmosphere at the end of the century, whereas the normal lifetime for an aerosol particle in the atmosphere is about a week. That means that once we start making mitigations to climate change, and we're already making mitigations to aerosol pollution because of their health effects, this cooling effect will go away and we'll get increased warming. So we really need to understand how large this cooling effect is to better predict future climate change. So how do aerosols affect clouds? Here's an image of some clouds over the ocean, mostly very thin clouds. And this is about 1,000 kilometers across, so it's a very large area. And you can see within this image, these large streaks of very thick reflective cloud within that. And one of them, which kind of is originating just here, if you looked at this location and zoomed in, you'd likely find probably a cargo ship or maybe a oil transporter, perhaps a cruise liner. These are caused by the pollution from ships' exhausts, burning incredibly dirty fuel. And these aerosol particles from this fuel enhance cloud formation. They form more droplets for water to condense on, which means you have smaller droplets, large surface area, more reflection. And more reflection of sunlight means more cooling. This is known as the primary aerosol effect, or the Toomey effect, and it's relatively well understood, although the magnitude of this cooling is still uncertain. However, the big uncertainty is what happens next. Now you've altered the droplets that make up these clouds. What happens to the clouds as a whole? Do you extend their lifetime? Do you extend how large they spread? Do you reduce rainfall because it's harder to form droplets large enough to start raining? Or do you increase evaporation, so maybe even shorten that lifetime? To the extent of the uncertainty we're talking about, we're not even certain for different clouds whether this will increase or decrease the lifetime of these clouds. And there's a lot of complexity about clouds. As Pierre Philippe said, one of the most normal ways to look at clouds and the climate is just through bulk statistics. Things like how much water is in a box of clouds like this? What's the average droplet size here? What's the density of droplets? But when we look at them in a high resolution satellite image like this, we can see there's a great deal of complexity. These are not just homogeneous grid cells. So we have several different patterns we can see. Down the bottom right, we have what's called closed cell stratocumulus. This is kind of very dense. Most of the surface is covered by clouds and they reflect a lot of sunlight. Up at the top, we have open cell stratocumulus, where there's these large holes in there, which means a lot of sunlight is getting through and therefore the reflectivity is reduced. We also have more broken structure and then a kind of break up to cumulus, where we have large clouds with gaps between them. And not only do each of these cloud structures change the amount of sunlight that's reflected, but they also change how the clouds evolve over time and respond to pollution. And so we really need to understand more of what's called mesoscale structure, so structure over tens to hundreds to thousands of kilometers of clouds, to really dig into how these lifetime effects will change. And we can see these kind of structures elsewhere. In this bowl of meso soup, you can see these similar patterns with blotchiness and structure with holes and brighter patches showing up. And it's all due to the internal circulations within, in this case, within the soup. In the atmosphere, it's within the lower parts of the atmosphere. And the challenge here, it's almost impossible to actually measure these circulations themselves without being, so to say, in the soup. And we can't do that on the atmosphere. The scale is just too large to get comprehensive measurements. Instead, what we'd like to do is try to gain some understanding of these circulation patterns based on observations of the clouds, and then use that to better understand how these clouds will evolve over time and how they're affected by pollution. So to summarize our science goal, we want to ask the question, how do aerosols influence the occurrence of different cloud types, and how do they influence the evolution and the transition between different cloud types over time? And our kind of hypothesis about this is that in a normal one of these marine clouds, you'd expect to start with this closed cellular structure and over time break up into open cells and then more broken, separated clouds. What we think might happen is that if we increase the number of aerosols, when it forms these closed cell clouds, it delays the formation of rainfall, and this delays the breakup of the clouds, which would be a cooling effect. But why is this difficult to study and understand? Why can't we just kind of observe a cloud type, make some machine learning classifier, and compare that to the measured aerosols? Well, the reality is it's a lot more complicated. There are a lot of processes within these clouds that link aerosols to cloud type, from droplet number density, feedbacks on precipitation, feedbacks on cloud properties, and also feedbacks on this circulation itself. So the clouds change the circulation that causes the cloud structure, and we can't observe this, which makes it very difficult to understand these processes from a purely statistical point of view. So how do we propose to go about this? Well, comparing to the state of the art, our first part is to change from a take of classifying clouds and observing clouds as just snapshots, single points in time, to a time-varying observation of clouds using geostationary imaging satellites. The second part is moving from classifications of clouds based on labeled datasets or unsupervised datasets to self-supervised classification, where we're looking for similar patterns in the clouds, not necessarily those patterns that we expect to see already. And finally, we want to move from this kind of statistical approach to analyzing these clouds to try and remove confounding variables by matching similar meteorological situations and looking at, well, can we find a similar cloud in high and low levels of pollution, to what's more of a causal analysis where we can actually say what happens if we were to change the aerosols within this cloud.
So at a high level, our pipeline consists of these 5 steps. We begin with manipulating our data, which, as we'll describe, we sample through time and space with a moving reference frame. We obtain a cloud type semantic segmentation with unsupervised and self-supervised learning. And we then use these cloud types in a supervised learning problem to estimate the causal effects of aerosols. We, of course, visualize our results, and we qualitatively and quantitatively evaluate them. We obtain a moving reference frame called a Lagrangian reference frame. This essentially allows us to follow a single air pocket through our data. It gives us these nice stabilized views of a cloud where we're confident that each pixel represents the same air mass frame to frame. This acts as a sort of Steadicam and allows our models to focus on the processes within a cloud rather than simultaneously trying to track pixels. This illustration that we're showing here also nicely shows one of the challenges with our data, which is handling these day to night transitions. We have wonderful optical and retrieval bands during the day, but at night we only have infrared bands, which we've shown as false color in these animations. To get around this, we've actually trained our models that we're going to show in this presentation only on these infrared bands, and handling this day to night variability is a great opportunity for future work. So let's get into the technical specifics of the pipeline. Beginning with our data, we have about 4 months of georeferenced satellite data from EU METSAT Severi sensor and meteorological data from ECMWF's ERA5 dataset and NASA's iMERGE precipitation dataset. We add to this about 4.5 million trajectories, which allow us to follow these air pockets through time. We sample these trajectories using a NOAA software called HiSplit, which we've cloned across 36 environments. In terms of infrastructure, we've made extensive use of the DGX supplied by NVIDIA and SCAN, as well as storage and compute provided by GCP. We developed 3 different models for identifying cloud types, 2 unsupervised models and a self-supervised model. We then use inference from these models to train an RNN for causal analysis of the effect of aerosols on cloud type transitions. And lastly, we have a suite of methods for evaluation and visualization of our results. Looking at our unsupervised models, the first one we use is to replicate the current state of the art from the literature, which is a tile-to-vec triplet loss model. Borrowing intuition from language models, it relies on the assumption that close samples are more similar than distant ones. The second model we implemented is an infogam, similar to a generic generative adversarial network, but an infoGAN gives the user some control over the features being learned by the model, which we've used to push the model into generating a fixed number of cloud types. Our self-supervised model is a bit of a classic idea, a mixture of experts, but with our loss function, we encourage each expert to specialize in identifying a specific cloud type. We then bring these embeddings together in the mixture assignment network, which chooses which expert to rely on for each pixel. And this is how we obtain a class mapping. These being unsupervised and self-supervised models, we need to very carefully design criteria to evaluate whether they've discovered meaningful cloud types. In our data, we have retrieval properties such as cloud fraction and liquid water path. And so we're able to evaluate whether our cloud types are developing intuitive clusterings based on what we see in the distribution of these properties within the classes. Now again, turning to our science question. What is the effect of aerosols on these cloud type transitions? We have a proxy for aerosols, and we now have cloud types, so can we answer this question? Unfortunately, the causal path between aerosols and cloud type is quite complicated. We need to adjust for the effects of these other observed and unobserved variables. But with many virtual whiteboard hours and the help of our experts, we've been able to find a backdoor adjustment that allows us to marginalize over these other properties, condition on local meteorology, and circumvent these unobserved circulation variables. What this looks like is we use our cloud types as targets in a supervised learning problem. We train an RNN to use as an estimator for different cloud type transitions, and we then integrate over the entire trajectory corpus to marginalize out meteorology, precipitation, and other aerosol effects from previous time steps. And now I'll pass it back to Will to talk about some of our results.
Thanks. So to summarize, we're going to go back to our pipeline and explain how you've achieved each of the goals we set out earlier. So starting off, comparing the segmentation from our three models, our baseline unsupervised models, and the mixture of experts, which takes more information in of the time variance of these cloud types. So the existing model that implemented into clouds, we applied to baselines this cloud Quebec. And we see this assumption that a neighboring tile is the same as the tile you're classifying, means that it struggles to distinguish similar cloud types when you have a steady change from one cloud type to another in the continuous variable. This is actually where the InfoGAN does a lot better because it doesn't make such assumptions. It just relies on a single tile and trying to identify the identifying features of that tile. And so it gets a lot more granularity. And then finally, the mixture of experts allows us to perform true semantic segmentation. So detection of type based on just the single pixel rather than a wider tile. And we see this has benefits in particular areas such as detecting the land and separating that from the rest of the image, which shows that it has a good degree of sensitivity compared to the other models we've implemented. We can then start analyzing when we take a trajectory, how do the cloud types change over time as we look at these trajectories? So here we have an example of following one box where we see a large number of trajectories plotted in the background. And we can see how the proportion of cloud types within one trajectory changes over time. We then use that to feed into a causal mixture model that allows us to predict what we expect the most likely cloud types for a trajectory will be. So here we can look at one trajectory as it passes through the atmosphere for about 3 days. And here's the zoomed in view. And we can see on the right a bar chart of the likelihood of various cloud types and how it evolves over the lifetime of the trajectory. So we have three main types here. We have closed cells in brown, open cells in purple, and this kind of broken up cumulus cloud in orange. And we see at the start of the trajectory, it starts out with a mixture of closed cells and open cells. It transfers more to purely open cells and then to broken cumulus, which is what we hypothesized in the first place for what we expect the trajectories to look like. Now, what we love to do in this situation is say, well, let's rerun this trajectory, but add a whole load of aerosols to the atmosphere. And that's something you could do with a climate model. But with observational data, you can't do that. We only have one planet to experiment with. So normally how you'd handle this is you'd study a large number of trajectories and you try and match them based on the initial conditions, things like the sea surface temperature, the humidity, and look for things, for trajectories that have matching initial conditions apart from the aerosol loading and see that vary. But using our causal model, we can predict what we'd expect to see in terms of cloud types for a different aerosol loading. So here we've told our causal model that what would you predict if the amount of aerosols in the atmosphere went from a relatively clean situation in the true data to something 10 times as large, so a very polluted atmosphere here. And we do see a significant difference, especially in the lifetime of these open cells clouds before the breakup of the clouds into this broken cumulus. And this shows that we're predicting a significant change in the lifetime of these clouds based on the aerosol loading that our causal network is trained on. And this is an important result because it means we can ingest observational data and then change the aerosol loading to whatever we want it to be and see what the wealth of our data predicts. So to summarize what we've done, we've looked at this data in these Lagrangian viewpoints, which allows us really to focus on the internal changes from the cloud. We've built classification models that classify the clouds over these trajectories, so not just a single point in time, but varying with time. And then we've used these to train a causal model that allows us to ingest real observational data and experiment with it as though we could change the settings as though it were a climate model. Why is this, we think, a really important result and a really powerful result? Is because it means we can perform these kind of experiments with real data. Previously, with climate models, you either have very high resolution climate models that can resolve clouds like these, but only have a short time period and a small spatial extent, or you have large global climate models which can predict the next century of global warming, but their individual grid boxes might be the same as this tile here, so they only represent these clouds as just a set of bulk statistics. Using a model like this, training observational data, means we can contain the complexity of these clouds at high resolution into some causal relationship, which we can use to examine how these clouds change over time with a changing aerosol environment, which allows us to look at the present day climate and say, well, what would happen if we removed all the aerosol? What would happen if we doubled all the aerosol or times it by 10 and perform these experiments using the observational data that we have today? So thank you very much, everyone, for listening. I'd like to quickly acknowledge the support we've had through this project. So particularly from the ESA Phi Lab, also from a number of domain experts from both the machine learning side and the clouds and climate side, who've been incredibly valuable wealth of knowledge, and also to the team at FDL themselves and all the partners who've made this project possible. So once again, with the Clouds and Aerosols team, thank you very much for listening.
Wonderful. Thanks so much, Clouds team. That was phenomenal and really amazing to see what you've been able to do. I wanted to throw it over to the panel now, Massey, Alison, and Julian, just to say, so what caught your eye, and then, as you were watching, any ideas that it sparked. Of course, there's a strong relationship between aerosols and weather. And then, implications, anything that, you thought would be sort of useful to feed back to the team.
Yeah. So first of all, such an education. So thank you. Thanks so much, Will, James, and also shout out to Tim and Lucas for fabulous work. I've been doing some personal study this week, actually, because of all the dry lightning that we've been having in the UK. So looking at cloud structure, and it's just fascinating. It really is. I love the fusion of so many techniques that you've used, and of course the thermal infrared for the fact that you can now look day out or night seems very trivial, but such a big change. And I can imagine a future where we're also fusing much more data from right across the electromagnetic spectrum. Actually, visual, for example, we're built for visual, but it's such a tiny fraction of the data that we can actually get from there. So pulling all that in, and there's tons and tons of work as well for thinking about deployment, mask, RCNN, for example, in very low swap for embedded, for intelligent satellites, for example. But I did want to say one thing that I read this week about causal effect and causal discovery. Similar work was actually published in Nature this week, improving clinical diagnosis. So take a look at that, and it's my opinion that this work deserves to be in Nature too. So excellent, thank you.
Thanks, Alison. So Massey, do you want to take the mic?
Sure, my pleasure. So congratulations. I mean, this is actually really exciting work. I want to second actually what Alison said around the fact that in integrating the idea of like very, very complex data processing with causal models, I think is really kind of the next steps in the way in which we will apply AI to kind of these very, very challenging problems. And I think actually you guys actually did something really beautiful here in the way in which those things integrated. But actually the other thing actually really caught my eye is that you didn't stop there, and you went actually into this kind of understanding these what if scenarios that I think is really kind of is where science is about. It's actually not just kind of understanding how things work today, but also kind of predicting how they would have worked or how they would work in the future. I think actually this is really, really promising. One thing actually that kind of I'm hoping actually you guys will continue to study and will kind of scale it out even more, because I think actually kind of one interesting aspect is to validate these models and potentially even kind of expand them even more by actually running them at a very, very global scale, and then actually kind of correlate actually maybe kind of what are the different percentages of aerosols and actually how actually those affect actually kind of meteorological weather actually at large scales, as you guys actually kind of pointed out in the introduction. So I'm really looking for how to kind of help you guys actually kind of expand this to even more massive scales. But again, congratulations, because this is really kind of awesome work.
Thanks, Massey. Julian.
Yeah, I mean, the real thing I'm missing today is the ability to clap in real time, because this is really, really excellent work, and you just want to hear the whole crowd clapping and join in. I mean, there's so much to love there, just like Massimo and Alison flagged, from the mixture, how you put together both the segmentation aspect, computer vision, then on top of that start to add some causality, modeling, and look at all that from a full time integration. So here, for the audience, there's a few bits that are really worth highlighting. First, moving from the snapshots to looking at the whole time process. There's so much information that the human eye or the human mind cannot comprehend when we are given a full time series of images like this. It's a bit like when you go to get a 3D scan for a CT scan of your body. The radiologist is going to look slice by slice, scrolling through the 2D slices with their mouth, whereas an algorithm can look at the whole volume in one go and get much more integrated view of the information this way. So what the cloud team has done here, by looking at the whole time series rather than independent snapshots, allows to precisely extract all this information in a way that the algorithms almost has an unfair advantage here. The use of unsupervised learning is, I mean, I'm a fan of mixture of experts. And when you put your slide, and we use a neural network to decide which expert, to me, I was like, duh, of course. It threw me back to 2008 when I was using mixture of experts with, very simple nonlinear activations. And it said, yeah, wait, of course a neural net. Why did I not think of that? So I really love this angle of mixing the old and the new to get something really powerful. And the unsupervised learning, I mean, much as a lot of the current tools that we are seeing on the day-to-day are based on supervised training, when you show the image and the label to the algorithm you're training, the real future is to tap into the huge amount of data for which you do not have labels. And that's where your team are going. That you gloss briefly over the marginalization of the circulation. And again, for the audience there, I just want to attract the attention on this little gem that just slides by almost unseen in the work, which is you got to your work, you got the causality model, and then you hit a wall. As in, oh, damn, the model depends on the circulation, and we do not have the data, and we cannot get it. And that's a point where, you know, a lot of people would just be like, well, we're doomed, what do we do? And you briefly allude to the hours on the whiteboard, and for having been in that kind of situation, I can see all the derivation there. And what's magic with this quick word of marginalization means, okay, we don't know squat about this data, about this behavior. You know what, let's integrate over it. Let's sum over all the probabilities, all the possibilities, and let's make a massive average on all that. And that is a real probabilistic thinking. That is a real power of both having to formalize it in a mathematical way where you're able to isolate this quantity that can be then integrated. But it's also the real thinking of, okay, let's look at the whole thing in probability and take into account all the possibilities. I really, really love that aspect. In terms of the next steps where you are heading with that, I mean, obviously the applications on climate change and on being able to, well, we're going to control the pollution, but in doing so, I mean, you scared the death out of me. You know, we're going to reduce pollution. We might actually heat things up. And it reminded me of a project that's ongoing at Oxford, who's looking at geoengineering. And that scares me. Okay, let's use geoengineering to put aerosols, silver aerosol in the air to make more clouds and avoid all of us completely frying right now. And there's a lot of debate around whether that should be done or not. But all your work here is going to be to allow domain experts to run what-if scenarios. There are some theories that geoengineering has been used locally during, say, the Olympic Games in certain parts of the world. There's a lot of question there, and tools like that you are developing allow precisely the exploration of these scenarios, both the worst case, the best case, and pretty much everything we can throw at these gigantic problems. So I can't believe you've done that in just 8 weeks. It blows my mind, and I can't wait to see the paper and to see all of that. So thank you very much.
Thanks, Julian. All right. Well, it sounds like we need a digital twin for Earth. I wonder if we should change gears and start looking at the next team.
Hi, I'm Ilan Rajas, CEO of Scan Computers. What an absolute honour it is to be recording this message for FDL. As a bit of a background, Scan is a loyal NVIDIA partner, and we've seen over the years the huge technological advancements NVIDIA has made in parallelization. Of recent, the mass steps forward that we've seen in data. And in many ways, in doing so many of our talks, I often liken data to nuclear energy. And there's a universe of data that's being collated and created, and it's growing at an infinite rate. And combine onto that computational capabilities, especially with all the efforts that NVIDIA have put in over the years, and how efficient that computational capability has now become and being able to be distributed. it was an absolute pleasure to hear about the project from FDL. So creating a digital twin, the Copernicus Earth observation, and being able to forecast chaos using compute and billions of data points really tests where computation can go. And what an amazing use case for what you guys are doing within the formation, predicting extreme weather patterns, disaster planning. It's ultimate predictability of chaos, which is such an amazing project, and we're absolutely stoked to be part of your initiative. And we'd love to donate and work with you in all the ways possible to help this kind of digital twin model come into some reality. The work done by NVIDIA, especially with the progression of GPU technology, especially with the new the DGX A100 and Ampere processing that's coming out there, with a whole ecosystem of ingest with fast networks and storage, is so groundbreaking that it's well warranted to actually work with FDL to combine both these technologies. We look forward to working with you, and look forward to seeing some amazing results. Thank you.
Well, good evening to everyone in Europe, and I guess good morning to anyone watching from the US. This is Team Digital Twin Earth. My name is Christian, and I'm super excited to kick off the final presentation. Now, let me first introduce my fellow researchers, Catherine, Daniele, and Valentina, and next our machine learning experts, Piotr and Freddy. And last but not least, our team leads, Duncan, who you've seen before, and Matt. And I think I'm speaking for all of us when I say it has been an absolute pleasure to work with all of you. Now, what is a digital twin, and why do we need one for Earth? Well, a digital twin is really just an interactive model that allows us to study counterfactual pasts, presents, and futures of our planet in silico. And as you're all aware, our Earth system is extremely complicated, and so trying to simulate it in full is somewhat of a moonshot. So for this project, we decided to focus on just one subtask: forecasting the global weather 5 days in advance. So why did we decide to focus on this particular challenge? Well, meet Rosie. Imagine she's a farmer in Uganda somewhere, and Rosie wants to wait for as long as possible before harvesting her crops in order to maximize the quality of her produce. Assume there's a hailstorm coming in, and Rosie only gets to know about it a day in advance. So in that case, probably up to a quarter of her harvest is going to be lost. But if she had 5 days notice, she could probably save most of it by going out and harvest. So we've seen that in developing countries, having access to accurate multi-day forecasts is a matter of livelihood. So how are we at the moment forecasting weather? Well, in terms of multiple days, the best method we know of is numerical forecasting. Now, unfortunately, we cannot just increase the resolution of our models in order to improve the quality of multi-day weather forecasts. And the main reason of this is because we are about to hit a hard ceiling when it comes to power consumption. We just cannot pay for the energy anymore that our machines are going to consume. And particularly in the developing world, it's not clear how this is going to scale. Unfortunately, all the other methods that we know of do not deliver the accuracy that we need when it comes to multi-day forecasts. So what are we going to do? Fortunately, the past years have seen incredible advances in neural network modeling. By learning physics from data, deep learning promises to achieve weather forecasting at far lower compute requirements. harvesting the power of deep neural networks does promises to lift the power ceiling that we are facing, and also to lower the bar for entry for countries such as Uganda, so they can run their own specialized forecasting services. So this is precisely at the heart of our project. We are using machine learning to learn data-driven weather forecasting models with lightning-fast inference. My colleague Daniela is going to tell you now how exactly we are going to do that.
Thank you very much, Christian. So first thing first, let's define the problem. We want to show how machine learning can help predicting precipitation up to a few days with global view to the Earth, including in the algorithm some kind of physical understanding of the atmospheric system. We can now focus on the single tokens in this statement. First, we decided for precipitation itself, since it is one of the most impactful atmospheric variables, especially in scenarios like roses. But how do we represent precipitation? Should we represent it in a numerical way with, let's say, values of millimeters of rain falling in an hour, or with a more humor-friendly representation like light rain, heavy rain, storms? And moreover, rain itself exposes some big challenges. It falls on a very small portion of the Earth at every single moment. And even there, light rain happens way more frequently than, let's say, a thunderstorm. And this leads to a very imbalanced learning problem. Next one is the future. How do we represent it? We can represent the future as a continuous series of predictions, let's say one every hour, or we can do a single shot prediction, asking the system to predict a specific date, like tomorrow at 5 p.m. And for how long should we aim to predict? A few hours is too short for most applications, just think about roses. And weeks in advance will bring in complexities way beyond the scope of the project. Few days, 3 to 5, is a good compromise for our study and for a usable application. Scale. So we aim for a global precipitation forecasts, but with local discretization, because at the end, no one interested in a precipitation averaged over the whole Europe. But you can see that the weather in the UK may be influenced by the weather above the US 3 days ago, right? So this fact brings in an overloading amount of data to be considered. And it is the order of terabytes of data for every single year. And we have many, many variables, from temperature to humidity to pressures. But at the end, maybe not all the variables are going to influence the precipitation, and maybe not even all of them are useful ones, since they can't be moved easily forward in time. This leaves us with the challenge of choosing the minimum set of variables that can allow us to achieve precipitation forecasting. And since we're dealing with the whole globe, we need to take care of the diverse landscapes, like land, sea, mountains will just behave differently, and we need to acknowledge that. And finally, someone could say, yeah, but we study weather since the last century, and we already have a lot of algorithms to predict precipitation. Isn't there a way to exploit them to help our system? We think this is a very good point indeed. Adding some level of physical understanding to the system will not only help our algorithm to learn a better representation, but it will also help the end user, since the system itself will be able to explain to some degree the Earth state it foresees, increasing the trust on the predictions. To do so, we decided to exploit the ERA5 dataset by ACMWF. This dataset contains hourly estimates of a large number of atmospheric, land, and oceanic climate variables from 1979 to 5 days ago. And as Christian described, physics is not enough to describe the evolution of the atmosphere. For this reason, we want to include also some notion of stochasticity in an algorithm, leading to the issue of choosing the right representation for it, either using statistical equations directly in the system or sampling different futures from the same present. This has a huge impact on the structure of the proposed solution. I will now let Katrin describe our proposed methodology towards the digital twin of the Earth.
So now I will introduce to you our proposed model of digital twin Earth for the task of precipitation forecasting. This system that we have designed will have three main components. Firstly, we'll consider satellite imagery that are coming from satellites, as well as atmospheric states coming from numerical models, in addition to precipitation maps over the globe. So how do these three main data components come together for precipitation forecasting? I will now walk through 3 steps that we used in our framework. Firstly, we start from satellite imagery to go to prediction and estimation of the atmospheric state in a data assimilation step. Next, we focus on the atmospheric state space, and we want to be able to forecast what the future state would look like. As a third step, we focus on the future atmospheric state, and we want to be able to reconstruct what the global precipitation map looks like in a post-processing step. So together, these 3 steps come together, and when performed in sequence, form the crust of our digital twin Earth model. So here we can go from satellite observations through atmospheric states to a future precipitation state. And importantly, we believe that the introduction of the consideration of atmospheric states helps adding in physical constraints to our model, which enables medium range forecasting for precipitation. This is a key differentiator of our method against traditional data-driven methods. And we believe that by doing so, we will be able to forecast in the medium range into the future for about 72 hours, or in other words, 3 days. In this FDL project, we have decided to make use of this framework structure to break down our experiments into 3 parts, each corresponding to each stage of this framework. In this case, we want to be able to show feasibility and demonstrate each stage independently. And I will now go on to describe how we precisely do that in detail. Firstly, this is a step that corresponds to the data assimilation step, and we'll consider a set of experiments that will focus on taking a sequence of satellite observations, as well as other observations which might be simulated from Earth that are available on the satellite. This is for the purpose of reconstruction of an atmospheric state at time equals 0, which is the present. As our machine learning backend, we consider the use of convolutional recurrent neural network for this task. In addition, we would like to stress that we are not just predicting a limited set of atmospheric variables such as temperature, but we are actually corresponding our intuition as well as different empirical results that suggested that we can predict a wide range of atmospheric state variables. This includes other variables such as cloud, liquid, ice content, humidity, amongst others. In our second step of experiments, we are focusing on the atmospheric state space. Here, we're looking at the problem of state forecasting. Precisely, we are taking in consideration a history of atmospheric states going up to 12 hours in the past relative to the present. And we want to be able to predict and forecast the state at a lead time of up to 72 hours in the future. As Danielle has mentioned, we want to be able to include stochasticity in our framework. And therefore, we have borrowed techniques from video prediction to include, to adopt a method called stochastic generative adversarial network for this step. So this completes our forward modeling step and the set of experiments. Our third set of experiments focuses on the same time step reconstruction of precipitation from atmospheric state. Here, we are considering the use of pixel-wise fully connected networks for this task. And this ties in nicely to the last step in our framework, which is the post-processing step at a future time of t = 72 hours. Now, this is a recap of how each of these set of experiments fit in together to form the whole picture of our digital twin Earth system. And I will now pass on to Valentina to explain how we are able to achieve feasibility in each of these.
Thank you, Catherine. Let's look at the preliminary results we had for each of these stages. Let's start from the state estimation, which given a set of observation of the Earth, which allows us to estimate the current state of the atmosphere. As Catherine said, for this step, we used a convolution on recurrent neural network so that we could feed into the model a sequence of observations, like the one that you see in the left-hand side of the slide, to output the single current state of the atmosphere. You see, still in the left-hand side of the slide, a comparison of the sequence of ground truth and the predictions of our model for two of the variables of the atmospheric state, the temperature one and the humidity ones. You can see overall that the model is able to capture the structure of these variables and also capture the specificities. For this task, no state-of-the-art data results are available, publicly available. This is why we compared instead different settings where we were feeding into the model different type of Earth observational data, but also some and also a third set where we were feeding in also the last available state of the atmosphere, which will be outdated a few days. Moving forward to the second stage of our system, which is the forecasting of the atmospheric state you can see here an example of the predictions that are made by our model. Here we needed to consider the chaotic nature of the Earth system. This is why we implemented a stochastic model for this purpose. And you can see, for instance, two different outcomes for our model over the area of Australia. Even though these don't differ that much, probably because for the time window 3 days, the possible state of the Earth don't differ that much between each other. We compared also our results with respect to reconstruction error that we get over time. For instance, if we look at the results we get for the temperature variable, you can see that our results compare very well with some baselines. For instance, they compare very well also with coarse operational forecasting systems, like the integrated forecasting system that you see reported here. But also we can see the value of using a stochastic system for this task, because when compared to the deterministic model recently proposed in the weather bench paper, you can see that we are able to improve over those results. Finally, our last step, which consisted in estimating the precipitation intensity given the state of the atmosphere. We tackled this task as a segmentation task by defining 4 different classes depending on the intensity of the precipitation accumulated over 3 hours, going from no precipitation to heavy rains. You can see here in small the ground truth for March 2019 and the predictions below that we had with our model. Overall, we can say that our model is able to capture the dynamics of this system, even though we don't feed into the model any temporal information. You can see also that our model is pretty accurate in distinguishing between rain and no rain. However, you can notice that it's a bit too confident in the heavy rain, it oversamples a bit. If we look at the F1 scores for each of these classes and compare it to the results of the ERA5 reanalysis dataset, you can see that our model can reproduce these results pretty well, apart from the drizzle class, which seems to be trickier to model. So the results that I just illustrated are for each of these steps individually. This is because the goal of our project was really to prove the feasibility of these tasks. Now that we achieved that for all the 3 stages, we can put everything together in an end-to-end system to really forecast the precipitation intensity given observation of the Earth. And now I pass it back to Christian to conclude the presentation.
Thanks, Valentina. So why do our results matter? Well, clearly, we have taken some exciting first steps in order to demonstrate that deep learning can help overcome the power ceiling that numerical weather forecasting is predicted to hit very soon. And here's a summary of our contributions. So before the past 2 months, there were no publicly available results on estimating some important state variables from simulated satellite data. Now we've got that. Secondly, we improved some of the publicly available benchmarks to do with state forecasting over a 3-day period, including results on temperature, and we added some new results on some of the so-called wet variables that are particularly strongly correlated with precipitation. And lastly, we also include a novel method of estimating precipitation from Earth observation data using neural networks. However, our contributions don't stop there. We are also going to open source a framework called PyRain, which we hope will enable future researchers in this domain to accelerate progress towards our vision of creating a true digital twin of our Earth. And remember, our overarching ambition is to provide 5-day forecasts, weather forecasts for the whole planet as soon as possible, so we can help farmers such as Rosie in Uganda. Okay, so I would like to conclude by acknowledging all the amazing people who have helped us with this project. These include, for example, Stefan Rasp and a whole host of other experts. Thank you so much for helping us during the duration of our project. And in addition, of course, I would like to thank our amazing partners and sponsors, and in particular, the University of Oxford and the Frontier Development Lab, but also NVIDIA and Scan, who have been providing us with some amazing DGX service, and the Google Cloud team, who has given us access to their resources. Thank you very much, everybody. Without your support, this project wouldn't have been possible. Have a good night.
Thank you so much, team. It was really exciting. I was getting text messages from my my climate scientist friends who were like raving about it as you were presenting, and really, I was so thrilled to see your results. So thank you so much. So again, I'd like to pass it over to our panel. You know, what caught your eye? What ideas were sparked? You know, what should the audience take away from this? And I think we're going to kick off with Massey.
Yeah, well, I'm kind of really thrilled about this work. And, you know, in a sense, actually, I think you guys have been really, really humble in presenting it. But this actually is massive progress. I mean, I think actually kind of really moving the bar in terms of using AI to not only kind of make better these simulations, but also make them, as you pointed out, cheaper so that they can be run at scale. I think actually is really kind of a path in the future. As you probably know, like there is a lot of momentum in this area from a lot of companies, including Google. And one of the things actually that really inspires me is this idea that we want to use technology in a sense to solve these big climate problems and these big kind of global problems. But at the same time, actually, we don't want to make makes that technology actually becomes a problem in its own by actually kind of consuming actually an immense amount of resources. And also there is another point that I want to kind of point out in this work that I think is really, really important. Right now, actually, this kind of technologies and capabilities, where they exist, are not really kind of accessible to a lot of like underdeveloped countries and people. And this kind of work actually can help democratize that. One point on the technical side of things that I think is really exciting is this idea of like having machine learning learning physics. I think actually that's really exciting. I have a physics background, and so on one side actually kind of I like actually my equations, but the idea of having machines being able to sift through this data and understand the behavior of natural world in a way that probably kind of we humans actually kind of cannot cope with, I think is super exciting. One last word that I actually would kind of mention here, I wouldn't kind of feel too bad about some of the kind of predictions not being on par with the state-of-the-art models. Those state-of-the-art models, just kind of to remind the audience, are usually kind of come back actually from like 60 or 100 years of research and iteration. We're really just starting with this, and you guys already kind of are almost on par on most of the metrics. So I think actually you guys should just give yourself a pat on the back and kind of I really kind of hope actually that this actually kind of continues and scales as you actually mentioned. Congratulations.
Thanks, Massey. Alison.
I love that you've focused on Rosie in Africa, and I'm actually doing a talk at a very big event based in South Africa, and I'm definitely going to be mentioning this. I happen to work with Maasai, and as symbiotic with nature as they are, they all have mobile phones, and when it gets to the stage that you can put this into an app, it will be absolutely profound, because for them, they generally don't have any water. And to know when to prepare for a massive downpour that you tend to get in, say, places like Amboseli in Kenya is just incredible. Back home, or actually in Germany, we've been working with some very big car manufacturers to do a digital twin of just their production facilities, so we can use lots of simulations and AI practicing in simulation prior to putting this into operation. And the fact that you can do this now on a global scale is just incredible. And then to be able to send that data via, say, a mobile app is incredible. And we're also, we've been doing for quite a few years now a lot of work with harmonic dwarfs, with ECMWF and the Escape project. So I look forward to working with you in the future to actually accelerate the mathematics with the GPUs going forward. Future work, and this would go for the clouds as well. If you're using LSTM, take a look at Sepp Hochreiter's upgrade to LSTM. He's basically put attention into the pipeline, and it'd be interesting to see some results, because when you're predicting 72 hours ahead, attention is really going to make a significant difference. So have a look at his latest hot field layers. But otherwise, fantastic.
Thanks, Alison. Julian, you've got the mic.
I'll try to be shorter this time, but I want to pile on what Massimo just said. Try to imagine how these models currently that do your weather forecast are developed. They are a massive bunch of equations that come from fluid dynamics, from wave motion, that are massive systems of partial differential equations that have been developed and honed over more than a century. You have entire labs, numerical analysis lab, who are focused entirely on trying to solve this huge set of equations. And so far, the best way has been to slice the Earth in little cubes and try to do some numerical propagation from one cube to the other. And that is 100 years of refinement, massive amounts of computation to be able to try to lower, to make these little cubes smaller and the approximation better. And now what you team have done, coming in and say, well, you know what, we're just going to ignore all the physics knowledge that's baked into these models, and we're going to throw a stochastic GAN at it, it really reminds me of my reaction on my first day when I joined DeepMind back in 2012. And I woke on my first day, and I've got Demis presenting, okay, yeah, we want to do, Atari action prediction. Like, hold on, you're trying to make a regression on a 30,000 dimensional space? That even possible? And there's very much the same feeling here. Like, you're gonna simulate the whole Earth and all the complex dynamics with again, without giving any physics way there. And so when you put this chart at the end where you're just the story beyond these two bars, which are just exactly on the same level with the UR5 model, physical model, and just next to it, your SGAN model with no knowledge of physics, with 2 months development, and they're the exact same level of precision. It's almost disgusting for all the people who've worked on this numerical model for years. I think that's really exciting because you are just at the very beginning, and I'm really looking forward to where you're going to push it.
Awesome. Thanks so much to our panel. Okay, so we're going to change gears slightly. Of course, the other infrastructure that we'll need to build a digital twin is a new era of Earth observation technology. And this, of course, means launching massive constellations into low Earth orbit. But of course, this is a problem for our friends in mission operations. And so we're going to talk about that now in a moment. So stay tuned and we'll see you for the constellations team.
Hi, here is Mission Control from European Space Operations Center in Darmstadt. My name is Alessandro Donati, and I have the pleasure to introduce to you today the FDL 2020 Constellation Challenge. Let's see together what is the background inspiration for the Constellation Challenge. We have a new operational scenario based of big constellations with fast increase of the number of spacecraft in orbit. As a consequence, the risk of collision between resident space objects is now dramatically increasing. Just to give you an example, in February 2009, a collision between Cosmos 2251 and Iridium 33 occurred. This event not only generated thousands of pieces of debris, but also heightened the international interest in preventing future orbital collision. Future potential collisions, or conjunctions as they are called, are predicted and warned using conjunction data messages. So, space debris avoidance is an increasingly demanding service which is provided by ESA. And the ESA Space Debris Office in ESOC, Darmstadt, is devoted to analyze the conjunction data messages and to identify and classify collision risks of European spacecraft. What is the objective of the Constellation Challenge? The key question is, can machine learning support risk assessment? The idea is to explore if we can use machine learning techniques to analyze conjunction data messages and to predict uncertainty evolution for an accurate, faster, and large-scale risk assessment. New models that learn uncertainty as it is happening will allow for a safer and easier ways to operate spacecraft in a complex environment. What are the expected data value? Well, the implemented machine learning algorithm will contribute to prioritize the focus of our specialists in assessing first the CDMs, that are classified with higher level of risk. So it's a question of combining expertise from our space debris office with the capability of machine learning to analyze and filter the conjunction data messages and to put in evidence the one which require immediate attention first. That's all from my side. Thank you.
Thank you. All right, so welcome everyone to the showcase of the work we've been doing for the past 8 weeks. We are this year's FDL Constellations team, and we've been working on applying AI to collision avoidance in satellite operations. So on behalf of the researchers, which are Francesco, Sarah, Francesco and Sarah from the machine learning side, as well as Jaco and myself from the space science domain side, we would like to thank our mentor team, Chris, Günesh, Sylvester, as well as from ESA side, Francesca, Jose, and Klaus for their amazing support throughout this research sprint. So spaceflight is the most exciting and challenging adventure humanity has ever undertaken. However, with every rocket launch and satellite deployment, we are creating a trap for ourselves that could end the space age and trap us on our planet for decades or even centuries. Objects in certain altitudes don't re-enter and burn up in the atmosphere anymore, but they stay in orbit around Earth for a long time. And after decades of space travel, low Earth orbit is now a junkyard of spent rocket bodies, dead satellites, and millions of pieces of shrapnel from fragmentation, such as collisions or explosions. Currently, we estimate around 30,000 objects larger than the size of an apple, more than 1 million objects larger than the size of a coffee bean, and around 100 million objects larger than the size of a Pfleet to be on orbit. Somewhere within this mess, there's also 3,000 dead satellites still orbiting Earth, and only around 2,300 active satellites can actually still be controlled. So objects in orbit are moving very, very fast. Nothing under 28,500 kilometers per hour can physically enter Earth orbit. And experiments have shown that being hit by one of the million coffee bean-sized objects can actually lead to material vaporizing, which releases the energy equivalent of a car hitting the wall at 50 kilometers per hour, or a hand grenade exploding right next to our satellite. And right within this danger zone, we also happen to have a $1 trillion global infrastructure network that performs critical services to us that we take for granted in our daily life. This is, for example, collecting weather data, or global communication, GPS, satellite television, and Earth observation, as well as a permanently manned space station where we can conduct experiments in microgravity. And losing access to space will not only set back some of our currently used technology back to the 1970s, but it will also hinder us from exploring our solar system and going back to the moon, leave alone dreams of eventually reaching Mars. And if business goes on as usual, the amount of objects in space will become more than tripled. So imagine 3 times this. Because when objects in space collide, the splash transforms them into clouds of tiny objects, which spread due to further collisions and different speeds and orientations, and eventually contaminate an entire orbital shell. Such collision cascades are known as the Kessler syndrome, and they result in a destructive domino effect where one initial collision leads to more and more collisions and an exponential increase in the object population. And now, right within this mess, large tech companies such as SpaceX, Starlink, Amazon, or Boeing plan to place mega constellations of satellites, each single constellation made up of more satellites than we actually currently have in orbit. So this will massively increase the burden on operators conducting collision avoidance maneuvers, which is why we start to think about ways to support this manual collision avoidance process in the future. But how do we actually take care of our satellites avoiding collisions with objects in space? So first of all, we can only avoid collisions with objects that we know of. So global space surveillance networks observe the sky and look for objects larger than the size of an apple, which they continuously track and update in a globally publicly available catalog. Then I, as a satellite owner or operator, can sign up for the collision avoidance service performed by the network, and then they would also observe and track my satellite, which is then referred to as the target. Observations are then performed every 8 hours, and positions and corresponding uncertainties are input into orbit propagation tools so that the positions of satellites and all other objects are fairly well known for the next 7 days. And to look for possible collisions, the target orbits are then screened against the object catalog population, which is then referred to as the secondary objects or the chasers. Within the screening process, the time of closest approach, or in short, the TCA, is determined as the point in time where the distance between the two objects becomes lowest. If such a conjunction happens, a collision warning message called CDM is automatically being sent to the owner-operator containing relevant information about the event. Then, over time leading up to the predicted close approach, observations are routinely being performed every 8 hours, and if the event stays alive, CDMs are being issued which contain also the current position estimates of both objects as well as the uncertainties which are necessary to perform collision risk assessment. Unfortunately, however, collision maneuver decisions have to be made at least 1 day before the estimated time of closest approach, where we are left with the information we have up until that point. And since each uncertainty has to be propagated to the time of closest approach, the first message we receive usually still contains a large uncertainty, and hence the information we have about the event is not very precise yet. With every new CDM being received, this uncertainty grows less, and we are provided ever more precise information about our event. Unfortunately, however, we don't receive updates on a regular basis, so the uncertainty evolution for a given event, as we can see in this plot for an example event, can be very dynamic and very hard to estimate due to not every object being observed all the time. So remember, we have to make a maneuver decision somewhere here where we still don't have the best information about the event and have to make costly and potentially dangerous decisions based on preliminary information. So what we would really like is a way of capturing this dynamic behavior of an event to be able to estimate its outcome and make reliable and accurate decisions. We think that data-based methods can help out here in learning such dynamic evolutions, and Sarah will now show us how we framed that problem.
Thank you, Sasha. Hi, everyone. My name is Sarah, and I'm a machine learning scientist. And in the next few slides, I will give you more details about the research questions we tackled during our FDL challenge. Okay, so the first question we must ask is, why is predicting the collisions risk so hard? The first reason is that characterizing the resident space object's behavior requires a thorough understanding of the interaction of the object with its environment, meaning that we need to propagate through time or predict all the states, parameters, and the energy level of the space objects. And it's well known within the scientific community that this problem has no closed form solution. The second problem is related to data, of course, because it's obvious that in order to use machine learning techniques and statistical inference tools, we need a lot of relevant data. However, with the space objects positions, these data are considered highly sensitive, and they have never been rendered public before. This changed actually recently when ESA decided to make public a subset of space objects dataset, semi-anonymized, of course, called the Kelvin's datasets. So the machine learning community can finally be able to tackle this challenging problem. So in this slide, I will go briefly through the risk assessment process just to pave the way in a better way for our research questions. And as discussed and described very well by Sasha before, in the low Earth orbit today, the density of space objects is increasingly high, meaning that the probability of collision with space junk mainly is higher than ever before. The current risk assessment process is quite manual, and it's based mainly on regular updates and regular data sent by the Space Network Surveillance Network, or GSPOC, based in USA. They send this kind of data in the form of CDMs, or conjunction data messages. And these CDMs contain, among other things, the time to the closest approach, the object's characteristics, and their corresponding uncertainties. And following the first CDM, there are a lot of other CDMs that follow in the following days with updated information. And the operator has to take all this information, all this data, and process it manually, assessing the distance between the target and chaser, assessing the uncertainties in the parameters. And at the end of the day, usually 1 to 2 days before the time to closest approach that was mentioned in the last available CDM, if the risk of collision is deemed important, a decision of maneuver or collision avoidance maneuver should be taken. So we see here that the current process is quite manual, quite heavy, and we understand that scaling the same manual process to the next generation space with this increasing number of space objects is completely impossible. Hence our two main questions. First, can we use machine learning techniques to predict the evolution of the CDMs, the conjunction data messages, in the future? And even better, can we use some generative framework to generate new CDMs and hence augment and increase the quantity of available data so the machine learning community can finally be able to tackle the problem and use more sophisticated and robust machine learning techniques? So in the next, or in the following slides, we will go through all the details about our modeling strategies. But first, let's ask this question. Can we use machine learning techniques to predict the high-risk events? So in order to answer this question, what we did is try different modeling strategies to do binary classification in order to detect high versus low-risk events, based, of course, on ESA Kelvin's dataset. One major challenge with the binary classification is the class imbalance. Of course, high-risk events being really low in terms of proportion compared to low-risk events. And to deal with this problem, we used very well-known and straightforward class imbalance techniques like oversampling and data augmentation. What we can see in the model's leaderboard is that even with the baseline model, we can get a quite high recall, whereas the precision is significantly low. And this same pattern is observed in all the models and the approaches we studied afterwards, whether it's using the last available CDM to assess the risk level in the last CDM, meaning at the time to closest approach, or more sophisticated approaches like LSTM or feed-forward neural networks to do the binary classification. Every time the recall is quite high, whereas the precision is low. And this is corroborated with the confusion matrix we see above, where the false positive is quite high. So the main takeaway from this first stage is that probably the risk concept is more complex than that. It's probably dependent on many other physical characteristics. And instead of trying to use machine learning to predict the risk directly, it's probably better to use machine learning tools to infer and study these physical characteristics as a proxy to understand or assess the risk level later. And this part will be tackled in more details by Francesco. Francesco, the floor is yours.
Thank you, Sarah. Hi, everyone. My name is Francesco, and in the next slides, we are going to answer one of the most important questions an operator would like to answer to, which is, can we predict the context of next CDMs given a few CDMs? Operators can observe only part of the sequence of CDMs, and in order to make a decision, they really would like to know the content of next CDMs. To answer this question, we use a specific kind of neural networks called LSTMs that have been successfully applied in natural language processing research. In this slide, we show a toy example in which an LSTM is trained to reproduce the word hello by predicting the next character in a word given the previous one. In this example, the LSTM is fed the H and predicts the E, then it is fed the E to predict the L, and so on and so forth. When the LSTM is trained to reconstruct a large dataset of words, it will eventually learn to predict a distribution of letters that can follow a given character in the alphabet and to reconstruct complete words. Similarly, we developed an LSTM that is trained to predict the next CDM given the current one. We can see it in action in this slide. In this picture, the CDM1 is represented by the blue dots. These are some of the variables contained in the CDM. The CDM contains around 100 variables. And our predictions on the contents of the next CDM are represented by these clouds of red dots. Now, we obtain multiple predictions because we are applying a Bayesian deep learning technique called Monte Carlo dropout that allows to produce distributions of predictions. But why operators do need distributions of predictions? The reason is pretty simple. Neural networks are uninterpretable models, and we would like to have a measure of how confident we can be in their predictions. And we can see that our model does not only capture uncertainty in the value of the variable, which is represented along the y-axis, but also captures uncertainty in terms of the time of arrival of the next CDM. In this slide, we can see it in action on many variables contained in a CDM, and we can see that an operator can feed our neural network with all the CDMs it has received, and then try to predict the content of the next CDM. But generally, operators would like to make decisions and have an idea of how the event will evolve in time with the least number of CDMs. Is it truly possible to do that with machine learning? Well, the answer is astonishing, and it is yes. It can be done in a very easy way with our model. Basically, we take our first CDM, we feed it to the LSTM in order to predict the second CDM, and then we feed the neural network this prediction itself in order to predict the third CDM, and so on and so forth. And we can see this model in action in this slide. Here, the blue dots again is the first CDM, and the red dots are the evolution over time of the values of the variables. And we can see that the neural network has learned non-trivial patterns, which as soon as new data arrives are confirmed. And we can see that this does not happen only on 3 variables, but it happens on most of the variables of the CDM. And in this plot, we can see that an operator can receive the first CDM, predict the whole sequence, the evolution of the whole sequence, and as soon as new CDMs arrive, repropagate the prediction in order to improve the accuracy. However, we need to quantify the performance of our neural network. And for this purpose, we designed a baseline that is a last value predictor, which means that the values in the next CDM are copied from the values in the previous CDM. This model achieves an MSE of 0.1809, while our LSTM, just by drawing one sample from the Monte Carlo dropout distribution, already attains a better performance of 0.1020. However, when we sample our Bayesian neural network multiple times, for instance, 30 times, the MSE drops to 0.0789, which is an amazing result. And the most interesting aspect of it is that our model can not only be applied on the Kelvin's dataset, but we have written it so that it can be applied on real-world CDMs, so that companies can take it and train it on their own private CDMs and test it on their own CDMs. However, the problem with neural networks, as we already said, is that they are uninterpretable. And for this reason, we considered whether it was possible to integrate a physical model in our machine learning pipeline. And I will leave the explanation of the details of this model for Giacomo. So I leave the floor to Giacomo.
Hello, everyone. My name is Giacomo, and I will guide you through the last part of this presentation. So as Francesco said, up until now, we have used an LSTM model for training on the Kelvin's dataset and predict the CDM evolution. However, we now ask ourselves, is it possible to incorporate the physics inside such type of models in order to have better predictions? So for doing this, we created a probabilistic model and we incorporated it in a probabilistic programming framework. So first of all, what is probabilistic programming? So a probabilistic programming framework is defined through a simulation, through a probabilistic model that is then used for making inference upon it. So first of all, statistical distributions are defined over the input parameters, which are then sampled forward for making prediction. So there is a first part in which the model is run forward and samples of output are generated. And once this is done, the model is actually reversed to make inference over the output data given certain input parameters. So in this way, we can get Bayesian posteriors, which is the probability of certain variables when certain evidence is observed. So how did this work in practice? So as we can see here in these images, we started sampling this model forward, as we can see from the moving dashed lines. And by doing this, we constructed 2 different probabilities. First of all, the probability of conjunction of the different variables that were leading to conjunctions, which is the orange one, and also the ones that were not leading to conjunctions, the blue ones. In this way, we could investigate the difference in the input variables when a conjunction happened or not. Also, as we can see here in these figures, we could also monitor the different variables as a function of the time to TCA. So for instance, we could investigate the geometry of the different orbits conjuncting, but also the different features evolving as a function of time. So all this was embedded in a probabilistic programming framework, and in particular, we made use of PyProb, which is a universal probabilistic program. And inside it, we built a space simulator. So this space simulator had a first part that was simply the sampling of the target and the chaser from given priors, and these priors were taken from realistic datasets. So once this was done, we had initial conditions that we could then propagate forward in time to get ground truth trajectories. Once this was done, as Sasha already explained, we made a screening process to check if a conjunction data message had to be released or not. If that was the case, then we moved to the ground simulation part. So in this case, we simulated the observation noise with associated uncertainties, and we made Monte Carlo propagation to propagate this noise up until time to TCA. So after this, we could generate a CDM, and the different series of CDMs were patched together to represent a conjunction event. So we made also a huge effort in calibrating this model with a realistical model. And in particular, we, first of all, selected the priors from the European Space Agency Kelvin's Discos Web, but also from the Celestrak databases. And also we made a tuning phase in which we tried to match as much as possible the propagated covariance with the one from Kelvin's, so that the observations noise is realistic. So all this, together with the LSTM predictor that was explained by Francesco, was embedded in a Python package that is now available open source and that is called Kessler. So we here show how to work with Kessler in a very simple way. So we can simply pip install it, and then we can use it for loading different CDMs and group them by events. And also, as we can see, the CDMs completely fulfill the CDM Blue Book guidelines. And we can plot the different features as a function of time, as well as use the synthetically generator for producing CDMs. So this will keep sampling the prior up until a conjunction is detected and a series of CDM is released. Also, the model embeds an LSTM predictor. So this can be trained on a series of CDMs that we feed to the network and can help us in predicting the next CDM given the one that we have, or also a different series of CDM as it was already explained by Francesco. So where do we go from here? As we can understand, the FDL 2020 research work opens up different paths. So first of all, the calibrated probabilistic model can be very useful for producing a very large synthetic CDM dataset. So we are talking about terabytes of data that can be used by the space and machine learning community for really paving the way for future research and for shedding more lights on conjunction events. Also, this model can be used in a Bayesian model-based inference framework in which posteriors over event evolutions can be studied and conditioned on given CDMs. Finally, this type of model can also be used to investigate physical aspects and key characteristics that have led to conjunctions, and this can be very insightful for operators. Also, the LSTM predictor of our Kessler package can be very important for private and public space operators and space agencies because they could train this LSTM with their own CDM datasets without actually making them public. So all this is available right now in the Kessler package, and as simple as it is, you have to just pip install it. So we really hope that our research has shed more light on the conjunction events and can make a step forward towards a more explainable and predictable collision risk assessment procedure. So with this, we would like to thank everybody for their attention, and in particular, we would like to acknowledge the help of the Space Debris Office, the FDL reviewers and administrators, and all the people that have helped us throughout this research period.
Great stuff, team. Thank you so much. I realize that's a lot of complex information to squeeze into a short period of time, and I thought you did an amazing job. So thank you so much. All right, I'm going to pick on Julian first. What are your thoughts? Any feedback, or what should the audience take away from what we've just seen?
There's a lot there, and it's almost cheating because my own research, a lot of it was in Bayesian machine learning and probabilistic methods. So the technological part here is really music to my ears. But first, I want to impress the importance of what the team is doing here. Because one could think, well, okay, traffic jam in space, collision in space. I don't drive in space. Why do I care? Now, I'd like you to realize what a Kessler event, the Kessler syndrome could be. That means a chain reaction of a collision propagating so far that by just a mere chain of, this little bit that breaks from this satellite goes into these other ones, breaks into more chunks that go into more satellites that regenerate more chunks, we have two problems. First, we lock ourselves on Earth, that we are literally putting a ceiling, a kinetic ceiling on top of us, and there's absolutely no way to go out of Earth. So that's if you're, Elon Musk or Jeff Bezos, you're going to be really worried about that. But okay, say I'm never going to go to Mars myself. Why would I care? If you just think of the amount of devices in your everyday life that is relying on satellites, and if you imagine suddenly losing all the satellites around us, this is an absolute nightmare. We suddenly lose all GPS, therefore all positioning, we lose all communication. This is just a nightmare scenario waiting to happen. So personally, I take huge solace in knowing that the ESA has a full team dedicated to monitoring these collisions. But I take even more solace in knowing that there are really bright minds who are looking at that. And for anyone paying attention, the latest announcements from the massive constellations from Starlink to Amazon we are going to be launching so many satellites. How are we going to keep them dodging themselves in the sky? Now, what the team has done here for me is they're bringing, I'm not going to delve on the Bayesian aspect because I'm just such a fan on the probabilistic aspect. I could bore everyone to death tonight for 2 hours. I promise I'm not going to do that. Instead, I want to emphasize the service that they are doing to the whole community and the whole field by putting this synthetic data set and this way to generate synthetic data out there. A dirty secret of machine learning is that we need massive amount of data. And it's not so much a secret anymore, but especially in the field of deep reinforcement learning, which is where DeepMind has been so successful with AlphaGo, with playing StarCraft, all these tools which are about control of complex dynamic systems, which are exactly the type of systems we are seeing with satellites, massively complex multi-agent systems. In order to be able to get any form of prediction and learning any form of control algorithm there, AI-based, deep reinforcement learning-based algorithms, we need synthetic environments. We need huge amount of data, huge amount of trajectories, even huge amount of data that we can generate conditioning on certain actions. So here, what you are doing by releasing this package is not just allowing a Kaggle competition to run on it, but actually allowing the methods around deep reinforcement learning and massive multi-agent control operations to be tried and unleashed on this problem. And I'm going to sleep a little better tonight knowing that you have put that out there. So this is a huge, huge service to the whole community and something that is not often emphasized enough. So thank you very much for your hard work.
Thanks, Julian.
Yeah, absolutely. Totally agree. And let's face it, we've already made a movie about this. So, massive shout out to our incredible atmosphere that burns up, who knows how much. And I'd personally love to know how this will help. And I'd love to hear from how this will help in scheduling, the many launches that are going to have to, try and safely move through this orbital minefield that you've showed us. But what's really interesting is that at the scale of objects currently in orbit, which is, rapidly increasing, it hasn't happened yet. That movie is still just science fiction. And that's because we're so good at this. But think how excellent the teams, Alex's teams at ESA Operations Center are going to be with this tool. He's no doubt rubbing his hands. And again, thanks to the explainability and the interpretability. Sorry, I've got a bit of feedback. So we literally have to, just say thank you for this, because you've also put that data set out there. And I love also the clear explanation of probabilistic programming, and also that you showed us the notebook. So many people really don't get what you're doing until they actually see the code at work. So, excellent move on showing that, and great name for the package too. I just want to take this opportunity though to say, very last thing, that this here all now is almost normal. And because of that, we actually forget that all this was accomplished by all of the teams now from home, separated from each other, from the team dynamics, but enabled by FDL's exquisite skills in building virtual camaraderie. So, hat off to absolutely everybody. Thanks.
So, and a shout out also from me. I just kind of to add actually to what both Julian and Alison said. I am a big space nerd, and the last thing actually I would love to see in my lifetime is us actually kind of getting locked in on Earth and literally clipping our wings by actually kind of doing something kind of not careful about these particular problems. So I think actually this is really kind of an important and inspiring work. I would love to kind of see more people going to space, and not only to Mars, but also to the moon, and actually kind of putting more and more technology there. I think it's changing our life, and it will in the future. On the technical aspect, one thing actually I wanted to mention is that I think this particular work is almost like a perfect segue to the first and the second one we saw today. As you took actually kind of the approach of the that was actually kind of in the second work around learning physics with AI, and you applied it to this problem very well. You also kind of went into probabilistic modeling that I think it's also very important, kind of understanding causality and probabilistic kind of estimation is very, very crucial in these kind of very complex problems. But actually, you also kind of did actually a step forward that I'm also very excited about. You went actually kind of and applied simulation. So basically kind of you went back to, our old traditional physics to kind of generate data and kind of bring this even forward. So I think actually kind of this is almost like a perfect kind of set of points that I think actually we should keep in mind for a lot of like models that we apply to science. This idea of inferring physics, this idea of probability estimations and uncertainty estimation, and then this ability of moving back physics into the AI by, for example, kind of applying simulations to generate data. So big shout out about all kind of this kind of approach and how actually kind of it can be impactful. One last thing actually I want to also kind of mention, as Alison said, I think the idea of open sourcing these assets and kind of opening them up to a much larger community of people, scientists and enthusiasts, to be honest. I mean, we are seeing actually a lot of people that are not maybe kind of traditional kind of researchers kind of getting involved today, actually thanks to the toolings and the availability of resources that we have. I think it's really great, and it's probably kind of could be actually kind of, and I wish it will, kind of a big transformational thing in this space. I hope actually kind of this work actually kind of really kind of continues in the direction Julian mentioned, for example, by actually also being used to kind of automate or maybe suggest the right decisions for operators in order to kind of reduce even more actually their load. So I think actually a really, really impactful work. I hope you guys will keep us in space, and congratulations again.
Wonderful. Thank you, Massey. And thanks so much for our panel. It was really awesome to get your feedback in real time, and really wonderful to have you join, and thank you for spending the time. So we have just a little bit more before we wrap. We have the awards, and I wanted to remind everybody, now you've seen the three presentations, as I say, just a bit of fun, but we have these available. But also, I would like to give our ESA stakeholders a chance to feedback. I think we're going to go to a small bumper now, and we'll set up the next session. Okay, thanks so much. Just wanted to again call out to our great teams, Clouds and Aerosols, Digital Twin for Earth, and Constellations. Really hope you enjoyed the sessions today, but also the incredible faculty team that support these researchers. Like, we really couldn't do it without you, and sometimes unsung heroes, but really fantastic support that you guys have given. So as I said, we'd really like to hear from our community. We have these fun awards that we give out, the most dramatic pivot, most useful contribution, and unexpected discovery. Now, we're using online voting tools to get to this. So you can either hold your phone up and go directly and quickly do it that way, or if you go to fdl.ai, the links are there, and we'll probably give it just 2 or 3 minutes, and then we'll go to the awards section. So please do. Now you've seen the work. It'd be fun to see what we think the results are from this. But I also wanted to give the opportunity for our friends and colleagues at ESA just to feedback a little bit. We have Alex from Mission Operations at ESOC, and Giuseppe from the Phi Lab at ESA Esrin, and just a few closing remarks, really, and love to perhaps give the mic to Alex.
Hi, James. Can you hear me?
Yeah, loud and clear.
Very good. So I'm really without words. I'm really been astonished by the results of the team, which undoubtedly make a game-changing vis-a-vis what can be done with artificial intelligence in mission operations. Sarah, Francesco, Sasha, Giacomo, you did a great job. Thank you so much. You know, in mission operations, mission success is the ultimate goal that we always perceive. And to reach that, one fundamental first stable step is to guarantee health caring of all our spacecraft. And as you point out, there is now more and more of these risks about collisions. And the amount of the way we are used so far to cope and analyze all the risks is not anymore sustainable by only humans. And with today, with this fantastic idea to make it open source, Kessler, you are opening a new way of dealing with assessing the risk, with increasing the health of all our spacecraft assets. I'm not talking about only ESA, it's worldwide. You have done a fantastic job. Congratulations, this is just a starting, but I see already that you pointed out also 2 different points that we need to solve. And another one, which was not mentioned by the previous speakers, but you did somehow, is what is called explainable AI. In mission operations, to have an adoption and acceptance, operators want to understand what comes out of a computation. And with this fantastic idea of picking up the probabilistic programming framework, in complementing the LSTM language model and the prediction of the CDMs, you are now not only providing the capability to generate a huge amount of synthetic data, but also to give them a physical quality of this data. Thank you so much again, and I hope the work will continue.
Wonderful. Giuseppe, are you there?
Yes, I'm here. Can you just confirm you can hear me, because my connection looks very, very bad?
Loud and clear.
Okay. So first of all, I want to say that I'm really excited to be here. I joined the Phi Lab very recently, a couple of months ago, so I'm a newcomer on this. But the things I saw today are really impressive. I was impressed about the DTE team, what they have done. The last 2 months I worked on DTE quite a lot, so I'm part of a team working on that. So I'm really excited to see all this kind of development. And so I worked on artificial intelligence about 20 years ago, so when was the so-called AI winter. So I'm really happy to see that now artificial intelligence is delivering great things, things that can be used. So I'm just excited to see what we can do together in the next period. So thank you very much for the team, for the great work that I saw today. Thank you very much.
Thanks, Giuseppe, and also to your colleagues at the FELAB who were there on every review and really provided great support and feedback for our teams. So again, please, just a quick shout out. If you haven't voted, still a little bit of time. And as a reminder, you can just go to the FDL.ai website and follow the links. It'll take you a few seconds. In the interim, we actually have some awards that we asked our faculty to vote on, just because really the insight required to give these awards was based on observing the teams over the 8 weeks. And so, Sarah, are you there to read the collaborative spirit?
I believe we've got a dropped call. Are you able to read that, James?
Oh, I haven't got the text. Okay. Oh, well, I can just talk to it. So basically, when we're celebrating or doing this sort of work, of course, it's about a collective genius and not lone genius. And so we're always looking for teams that figure out how to get to this sort of some of the parts which was greater than just going it alone. And so we asked our mentors and faculty to look at the teams and say, well, which of the teams or which of the individuals really embodied this concept of collective genius. And here are the results. We've got someone typing. I don't know if that's, sorry, there's a little bit of audio there. So let me reveal what the collaborative spirit results are. So we actually have 3 joint winners for collaborative spirit, and I wanted to call out Sasha and Giacomo. Really, this sort of ability to bridge the gap between machine learning and space, and you really, both of you, took the time and took the time to educate all of us on your knowledge in an excellent and very clean and clear manner. And so our faculty thought that your abilities here really were deserved of the collaborative spirit. But also, again, joint winners of this award, the Clouds and Aerosols team, and the feedback we had from our faculty was really impressed with just how the team member got along and were willing to work on multiple parts of the project and just purred through the project working selflessly. So, and they're an inspiration, which is a lovely bit of feedback from our mentors. So, so that's the first result from the collaborative spirit, and I'm hoping that Sarah will have jumped on by now.
I'll say keep rolling, James.
Keep rolling. All right. So, so the next award from our faculty is the Heroic Comeback. And really, this is this award here is the Apollo 13 mission, which of course is NASA's finest hour, and we've embodied this award in this story of Apollo 13. And of course, we're doing high risk, high reward work. It is really difficult, this stuff, and sometimes when you're trying to do new things, it's easy to get lost and easy to lose your way a little bit. And so, we really like to celebrate teams and individuals that are able to face the fear and come through those difficulties and come out the other side with an extraordinary result. And so this is the Heroic Comeback Award, and let's see what the faculty decided. So it looks like we have the Digital Twin for Earth team and Catherine Tong as joint second place. But Sarah Bafella from the Constellations team, congratulations for your heroic comeback. I mean, I know really you had a very, very difficult summer with lots of demands on your time, and we just wanted to acknowledge the extraordinary work that you've done for us, and say thank you so much for digging deep, and also balancing everything that you've had to do. So those are our two faculty awards, and so let's now, hopefully in the interim, we'll have had some people coming to vote, and we can go to the most dramatic pivot. And so looks like Sarah's unfortunately had to jump off, so it looks like I'm going to have to again wing this. So apologies. The most dramatic pivot, this award, again, is sort of symbolized by this asteroid being moved off course. This is when a team realizes that they have to change their direction. And it can happen at the beginning or the middle or the end. But it is, again, sort of a byproduct of doing stuff which is new. We say at FDL, if it isn't hard, then it isn't new. And so this is something that we celebrate with this award. And hopefully, if I click on this, we're going to get teleported to the audience vote. And let's see what happens here. So hopefully, is everyone able to see my screen?
Yes, we can see it.
Great stuff. So let's see what happens. So most dramatic pivot. Wow. Okay. All right. Well, congratulations to the Constellations team. That is really great to see. And obviously the audience were impressed with the journey that you went on. And so let's go back to where we were. So, right. So this, the next award, and I'm very relieved that that worked. So thanks to everybody who helped make that happen. All right, so the next one, the most useful contribution. So this really speaks for itself and is celebrated by an astronaut carrying another astronaut. But of course, it's not just the scientific contribution. When we are talking about the work of machine learning for space, we're also interested in the huge amount of work in data preparation, creating modules and tools and workflows for the community and sharing them for the community, and making tools available for public good. And so this award, we'll see who this has gone to. So let me click on this and teleported to the results. And so the most useful contribution award goes to the Constellations team. So again, Constellations team, really wonderful to see that. And I'm hoping that other teams will get some awards too. It's not meant to be a clean sweep, but obviously a lot of people thinking that what you've achieved is extremely useful. So the last award we have is the Unexpected Discovery Award, again symbolized by this this planet, which has got 3 rings around it. And as mentioned, we're in this really amazing moment where machine learning is becoming a tool for science. And now that we have really robust methodologies for explainability, rather sort of than being an interesting thing or a toy or a sandbox exercise, because we can explain what the machine learning is doing, we have the ability to start using it as a tool for empirical discovery. And this is the transition that we're going on at the moment, where machine learning is really becoming, as important as other tools like microscopes and telescopes in terms of doing science. And so we like to celebrate this at FDL. And so let's see what the audience thought. So we're going to the unexpected discovery, and that is constellations team. Again, congratulations, constellations, and commiserations to Clouds and Digital Twin. I don't think this is certainly not meant to be representative of the merit of your work, but more a fun thing. Again, thank you to everybody who voted tonight. So with that, we're going to start wrapping up. I just wanted to shout out to a few folks. I mentioned the team at the Phi Lab and of course Francesca and Jose and Klaus at Mission Operations. I know there are lots of individuals who were there, week in, week out, supporting us, our amazing machine learning community from Oxford and other places, who again lending their wisdom and just helping our teams to refine and find better angles on their work. But we really, we're so grateful to our community, and we couldn't do this work without you. So I wanted to quickly say thank you for everybody who's come along on this journey. Also, we have one last award, and this is a new award for this year. We wanted to celebrate, I guess, our faculty, because we now have faculty members that have been with us for a while, and really, even though, as I said, they're behind the scenes, they're very much front and center, and often, coding in the middle of the night with the researchers themselves. And so this last award we're calling the Steely-Eyed Operator Award, and we have a little film that I want to show you just to celebrate this. So can we roll the Apollo 12 film?
November 14, 1969, Apollo 12. Astronauts Pete Conrad, Dick Gordon, and Alan Bean are headed for the second moon landing. The need to make a fast decision is about to fall on controller John Aaron. He's in charge of electrical and environmental systems. His call sign, ECOM.
The thing that makes a good ECOM is a natural curiosity about how things work, even if you are not responsible for them.
2, 1. Ignition Apollo 12 lifts off. It's Jerry Griffin's first launch as flight director.
And all of a sudden all the data went away, and there was a big static in my headset.
What the hell was that?
I said, ECOM, what do you see?
I looked down at all of my telemetry data, the readouts from the spacecraft, and they were nonsensical.
In the spacecraft, astronaut Alan Bean has no clue either.
Just lost the platform, gang. I don't know what happened.
Lights pop on. The alarm system comes on. More lights than I'd ever seen in the simulator. I mean, there was main bus A, main bus B.
I got 3 fuel cell lights, an AC bus light, a fuel cell disconnect, AC bus overload, 1 and 2, main bus A and B out.
It's an electrical failure. The command module has lost main power. Emergency batteries take over, but they'll only last 2 hours. Mission Control is facing a launch abort, jettison the spacecraft, and blow up the Saturn V. Now John Aaron's curiosity pays off. A year earlier, during a test, he had seen a strange pattern of data. and had learned about an obscure switch inside the command module that could fix it.
I had seen that pattern before, and it had been 1 year since I had seen it. But it was like that pattern was written in my mind.
The Saturn V's engines keep burning, but the command module on top of the rocket is barely alive, powered only by emergency batteries. Everyone expects ECOM to abort. Then Aaron makes a different call.
I said, Flight, tell them to take the SCE to AUX.
Flight Comsat, SCE to AUX.
And I said, what?
Say again, SCE to AUX.
SCE to AUX.
I said, what's that?
It was some obscure switch, signal conditioning electronics to auxiliary.
I turned to the Capcom and Jerry Carr, and I said,
SCE to AUX, Capcom.
And Carr said, what?
Mission Control comes back and says,
Try SCE to auxiliary, over. SCE to auxiliary. SCE to auxiliary. What the hell is that? SCE to auxiliary.
Turned out Al Bean knew where that switch was. It was back over his shoulder. He threw the switch and we got all of our data back and we could see what the problem was.
We got it back, Flight. Looks good. Okay.
Later analysis reveals Apollo 12 had been hit by lightning, which traveled down the rocket's exhaust to the ground, knocking the spacecraft's main electrical system offline. The obscure SCE switch wasn't designed for this situation, but it works.
thank God for Mission Control. Thank God for Mission Control. I didn't have any idea what to do.
Pete Conrad broke out in nervous laughter.
You know what it did? I know what it is.
He laughed all the way into orbit.
I never saw somebody light up the pillar so many lights before I couldn't read them all.
So hopefully everybody enjoyed that story of Apollo 12 and when it was hit by lightning early on in the mission. And you'll see the econ operators and mission control had this error which came up, which said no solution. And, you know, sometimes this happens. Sometimes when we're halfway through a challenge, suddenly things get really tough, and this is when our faculty are invaluable, and it means rolling sleeves up and diving in and rescuing a project, just like on Apollo 12. And actually the individual who rescued that mission, this is where we have the phrase steely-eyed missile man, and this happens with us too, and we wanted to acknowledge somebody who's really done this again and again for so many projects, has been there through thick and thin, and often not really getting any acknowledgement. So we wanted to take a moment just to say thank you. And so the award for the steely-eyed operator goes to Gunas. You've been a fantastic, amazing team lead and done extraordinary work for us, and just wanted to say thank you so much. We'll make sure you get a 3D printed steely-eyed operator award, but really just again to say thanks for everything you've done. So just to wrap up, again, I wanted to say thank you to the team at Google and NVIDIA and SCAN. As we've said, the work we do here is completely dependent on the huge resources that you bring. And thank you so much for your time and passion as well. A quick shout out to the Phi Week. Our colleagues at ESA Esrin are running the Phi Week on the 28th of September. Please, this every year is a fantastic celebration of Earth observation and AI. And this will really, give you if you're interested in these two, the collision of these two domains, this is really the best place to go to get up to speed. I just also wanted to thank you to our hosts, of course, University of Oxford, really providing the extraordinary academic backbone to our work. Our friends and colleagues at the SETI Institute, who we work with day in, day out to make FDL happen. And of course, our colleagues at Earth Coast, who provided this broadcast and made it run so smoothly. Lastly, also wanted to say a quick thank you to the amazing team at Trillium for working so hard. Pulling this off and making it look seamless is quite an incredible thing. And I'm really grateful for all your hard work and the countless hours required to get to this point. So that's our show. I really thanks so much for joining. I hope you learned something. I hope there was some inspiration as well. And we'll hopefully see you again tomorrow. We'll be doing this again with the team at NASA. This is running on the same website, so fdl.ai. So please tune in. And otherwise, we'll see you next time.